Today we have taken up the title as the units in a ring. This comes in the section ring theory from the chapter algebra, and questions are coming from this topic, units in a ring, in TS set examinations. 1 or 2 times it has come, and today's lecture is suitable for all the aspirants of JL, DL, TS set, AP set and CSR net examinations. Right. We start our discussion, by the definition of a zero divisor. For that, we have a ring R, and a non-zero element A of the ring R is called a zero divisor. If there is a non-zero element B in R such that AB is equal to 0, or BA is equal to 0. So we have A belongs to R, A is not 0, then that will be a zero divisor. If you have another element, non-zero element B in R, such that the product either AB is 0 or BA is 0. So such an element is called zero divisor. A is a zero divisor. If A is a zero divisor, then B is also a zero divisor. Right. Now, the next one, we take up the definition of a unit. You see, for this, we first of all have R is a ring, commutative ring preferably, or ring with unity. Unity is 1, not equal to 0. So don't get confused by the terminology. Unity is the identity element. Unit is different. So an element U of the ring R is called a unit of R, or unit in R. If there is an element V in R such that the product UV is equal to VU is equal to 1, then U is said to be a unit. So who are the units? Units are invertible elements. If they have inverse, then they are called units. And the set of all units of a ring R is denoted by R superscript X, or cross. R, U of R. U of R stands for units of R. Agreed. So, and we have already studied in our MSc classes that the set of units of a ring R, they form a group under multiplication. So R superscript cross will be referred to as the group of units of R. Right? So the units of the ring, very famous, is an integral domain, Z plus dot, units of the integral domain of integers. What are the units? Who are the elements which admit inverses, multiplicative inverses? They are plus or minus 1. So it has only 2 units. And every non-zero element of a field is a unit. Right. The units in the Gaussian integers, Zi, what are Gaussian integers, Zi? Zi is the set of all those complex numbers A plus IB, where A and B are integers. So such a set, that one forms a ring, commutative is a ring with unity, and that ring is called Gaussian, the ring of Gaussian integers, and the units are, there are 4 units which we have studied, plus or minus 1 and plus or minus I. Right. Now, suppose you talk about a polynomial ring where R is an integral domain, let us say. R bracket X means the set of all polynomials with the coefficients coming from the integral domain R, right? And they are polynomials in X and the coefficients are coming from R. And who are the units of that one? The units are just the elements of R. The elements of R are the units. Non-zero elements of R are the units. Agreed. Now, suppose you talk about the direct product of 2 rings. Let us say R is a commutative ring with unity. S is a commutative ring with unity. You talk about the direct product R cross S. And what are the units in this R cross S? It will be the set of all those ordered pairs A comma B, where A is a unit from R and B is a unit from S. That, in other words, it is said as the units in any direct product of rings are the elements that have units in each of the coordinates. Each of the coordinates means each of the components. If it is R cross S, the ordered pairs A comma B, A is a component and B is another component. There must be units of that one. Agreed. So these are some of the facts about units. Right. So we talk about now the zero divisors and the properties of some of the zero divisors. So we have a R, a commutative ring with unity, and this is the result what we want to talk about. That is, if A is a zero divisor in R, then A can never be a unit. Then A cannot be a unit. If A is a zero divisor in R, then A cannot be a unit. What's the proof? We have A is a zero divisor in R. So it is a zero divisor means it is a non-zero element, and there is another element B which is not equal to 0, another non-zero element B in R, such that the product AB is equal to 0. Or BA is equal to 0, but for simplicity we have taken AB is equal to 0. Agreed. Assume that A is a unit in R. We want to prove A cannot be a unit, therefore we are assuming, a false assumption we are making, that A is a unit in R. What do you mean by A is a unit in R? There exists a V, a non-zero element in R, such that VA is equal to AV is equal to 1. Agreed. Agreed. Now, to get a contradiction, we argue like this. B is equal to 1 multiplied by B. Yes, 1B is B. For 1, we write VA. So, VAB. Use the associative law, then you will get V of V multiplied by AB. But what is AB? AB is 0. V into 0 is equal to 0. So this is, you are getting B is equal to 0. But what is B? B is a non-zero element. So in the definition of a zero divisor, B is not non-zero element. So thus we get a contradiction. This contradiction is due to our false assumption that A is a unit in R. Therefore, A is not a unit. So, if A is a zero divisor in R, then A cannot be a unit. Right. Similarly, suppose for a zero divisor, you have taken AB is equal to 0. Suppose you are in your argument BA is equal to 0. For some non-zero B, then A cannot be a unit. Similarly, you can also prove. Now, you take, this is a fact now, this is a result, and this is true, and you take the contrapositive statement of this result. What is the contrapositive statement of this one? If A is a unit in R, then A is not a zero divisor in R. So because this statement is true, therefore its contrapositive statement, this result is also true. That is, if A is a unit in R, then A is not a zero divisor in R. So this follows because it is a contrapositive of the above true statement. Agreed. Now, can we have an element in certain ring R which is neither a zero divisor nor a unit? Our above result says a zero divisor can never be a unit, right? So can you give a non-zero element in certain ring R which is not a unit and not a zero divisor? Yes. We can very easily give. So take the example of Z plus dot, the ring of Z plus dot. Who are the units? Plus or minus 1. Right. You take any non-zero element, let us say 2. Is 2 a unit? No. The units are plus or minus 1. And is 2 a zero divisor? No. 2 multiplied by what element will give you 0? No element. So 2 is not a unit. 2 is not a 0. Thus, we have elements in a ring that are neither zero divisors nor units. Right. Consider this is a counterexample. Z plus dot, units are plus or minus 1. Note that you take any element from Z minus 0, 1, minus 1. So, non-zero elements other than 1, minus 1. And any element is neither a zero divisor nor a unit because this Z plus dot has no zero divisors. It's an integral domain. So that's the example. Right. We move on to an example 1. Right. So this is an example what we have created for you. Let R and S be two commutative rings with unity. Which of the following statements is not true? The first option is option 1. The units in R form a group under multiplication. Yes, it's a fact. The set of all units of a ring R, commutative ring R with unity, they form an abelian group under multiplication. This is true. Second, every non-zero element of R is either a unit or a zero divisor. This is not true. This is true only in Zn. This is true only in Zn. And we have given an example. That is Z plus dot, where there are elements which are neither zero divisors nor units. So every non-zero element of R is either a unit or a zero divisor is wrong. Counterexample is Z plus dot. We have already chosen. So option 2 is not true. Option 3. The units of R cross S will be given by the set of all ordered pairs A comma B, where A is a unit of R, B is a unit of S. This is true. And the units of Mn R, that means the set of the ring of n by n matrices with the entries coming from R, where R is a commutative ring with unity. It is also a commutative ring with unity. And what are the units of Mn R? The invertible elements. That means the invertible n by n matrices with the entries coming from R. That is precisely the general linear group of n by n matrices with the entries coming from R. That is GLNR, which we have already talked about this one. So the answer to this question is option. Agreed. Now we take up an example, example 2. We have R, the set of all 2 by 2 matrices with the entries coming from the integers. And this R is a ring with respect to addition, usual addition, and multiplication. This is not the multiplication is not the matrix multiplication, but it is a component wise multiplication given here. I will show you. This is the component wise. This is the addition of matrices. This matrix multiplied by another matrix is the component wise multiplication. That means A11, B11, second element, A12, B12, A21, B21, A22, B22. That is the multiplication. Right. Under this, it forms a ring. It's a commutative ring. It's a commutative ring because the commutativity also comes here, because it's not the matrix multiplication, mind you. So, commutative ring with unity. What are the number of units of such a ring? Or 4 options are given to you. Agreed. And for the above ring, the unity element is 1, 1, 1, 1. What is a unity element? You take 1, 1, 1, 1, multiply by A, B, C, D. Use this result. 1 into A, 1 into B, 1 into C, 1 into D. That is A, B, C, D. So this is a unity element. Right. Now, let us say A is equal to A, B, C, D is not a zero matrix, belongs to R, is a unit. What do you mean by that? There exists a B, a 2 by 2 matrix, P, Q, R, S, coming from R, which is a non-zero element, non-zero matrix, coming from R, such that the product AB is equal to 1, 1, 1, 1, the unity element. And take the product, A means A, B, C, D, B means P, Q, R, S, and multiply 1, 1, 1. And if you multiply, here it is component wise multiplication, not the matrix multiplication. It is AP, BQ, CR, DS is equal to 1. So that means AP is equal to BQ is equal to CR is equal to DS is equal to 1. Who are A, B, C, D, P, Q, R, S? They are integers. But when they are integers, AP is equal to 1 will give you, what are the possibilities? A is equal to plus or minus 1. So, A is equal to plus or minus 1, B is equal to plus or minus 1, C is equal to plus or minus 1, D is equal to plus or minus 1. So, that means the units of R are matrices A, B, C, D, where the entries A, B, C, D belongs to the set consisting of 1, comma, minus 1. How many units are there? Use the product rule of counting here. A takes values 1, minus 1, 2 choices, B 2 choices, C 2 choices, D 2 choices. Therefore, the number of units are the number of matrices, and that will be 2 into 2 into 2 into 2, that is equal to 16. So, the answer to this question is option 4. So, that is the detailed discussion of this example. This example is definitely a good example. Agreed. Now we change the scenario. And until now, we were talking about arbitrary rings. Now we talk about Zn, units of Zn. Zn is a commutative ring with unity 1. The set of units of Zn, who are they? What is Zn? Zn is the ring of integers modulo n, and the set of units of Zn are denoted by U of n. And note that U of n is a set of all positive integers less than n, which are relatively prime to n. That means it is the set of all those A belongs to Zn such that the GCD of A comma n is 1. Further, and the set of all units form a group, and here it forms a group under multiplication modulo n. Under multiplication modulo n. And what will be the order? The order of un is equal to how many elements of Zn are there which are relatively prime to n? They are phi of n, where phi is the Euler's phi function. Agreed. So the number of units of Zn, what is Zn? It's isomorphic to Z by Nz. It's a quotient ring. Quotient ring is order of un is equal to order of un is phi of n, where phi is the Euler's phi function. You know how to compute Euler's phi function. Right. A belongs to Zn will be a unit when, if and only if, the GCD of A and n is 1. A belongs to Z is not a unit if and only if the GCD of A and n is not 1. So, in Zn we have this property. In Zn, not in any ring, in Zn, every non-zero element of Zn where n greater than or equal to 2 is either a unit or a zero divisor. This is a very important result here, but this is not true in general in rings. We have already discussed that. The counter example is Z plus dot. We have already. So if you use this fact, you can also count how many zero divisors are there. So the zero divisors of Zn are given by Zn star minus the set of units. Zn star means non-zero elements of Zn, because zero divisors are non-zero elements. So Zn star minus u of n. So that means you take Zn star, from that take out the units of Zn. And why it is so? Because in Zn, every non-zero element is either a unit or a zero divisor in Zn. So now the number of zero divisors of Zn can be counted now. That is mod of Zn star minus mod of un. Mod of Zn star is non-zero element 9 minus 1, n minus 1, minus order of un, number of units in Zn is phi of n, where phi is a Euler's phi function. Thus we have a formula for that, right? So an examiner can exploit this fact. So we move on to example 3. So this is an illustration what I make it. You consider Z14, right? So how many units are there? We talk about how many, if you ask ready-made, the number of units in Z14 is given by phi of 14. What is phi of 2 into 7? And phi of 2 into 7. 2 and 7 are relatively prime. Therefore, phi of 2 into 7 is phi of 2 into phi of 7. What is phi of 2? Phi of p, where p is a prime, is p minus 1. So 2 minus 1. Phi of 7 is 7 minus 1. And that is precisely 6. This is the number. If you want, you can do that. But you can also physically find out who are the units of Z14. That means catch hold of all those elements of Z14 which are relatively prime to n. So the units in Z14 is U14, and it is a set of all A belongs to Z14 such that A comma 14, the GCD of A and 14 is 1. So who are all those A's? Is 1 a unit? Yes. 1 comma 14 is 1. Is 2 comma 14? No. 3 comma 14? Yes. Like that. 5 comma 14? Yes. 7 comma 14? Yes. 9 comma 14? Yes. 11 comma 14? Yes. 13 comma 14? Yes. So these are the 6 elements. So 1, 2, 3, 4, 5, 6 elements. So you can physically count if because Z for Zn where n is small, therefore you can do this one. Suppose if n is a big one, the number will be counted using the Euler's V function. That I will show you in the next example. So the number of units in Z14 is 6 by this also. So talk about the zero divisors. So now the zero divisors of Z14 are given by Z14 minus the set of units of Z14, that is U14. So from Z14 star minus U14, if you substitute, then you will get the even ones, 2, 4, 6, 8, 10, 12. Right? You can physically do that. So that is the thing. And since in Zn every non-zero element is either a unit or zero divisor, therefore we have subtracted the units and the remaining ones are zero divisors. Now the number of zero divisors of Z14 are Z14 star minus order of U14. And that is equal to Z14 star is 13 minus order of U14 is phi of 14. What is phi of 14? It is 6. So 13 minus 6 is 7. So these are the, physically you have done those zero divisors, they are 7 in number. So thus you get the 7 also. So either way you can do that. So now we go to a question that has come in TS set 2019, and it's not counting, it is on units. It's on units. Question number 72 and question ID is this one. What is that one? The number of units in the ring Z by 8Z, that means Z8 is, we are given 4 options. Great. Now solution. And we have Z by 8Z, which is isomorphic to Z8, the ring of integers modulo 8. Right. The number of units in the ring Z by 8Z, the quotient ring, is isomorphic to Z8, is given by phi of 8. 8 is, for 8 you have to write the prime factorization, phi of 2 cube. And phi of 2 cube formula, 2 cube into 1 minus 1 by 2, that is equal to 4. So therefore the answer to this question is 4, and that is given against option 2. A very simple question. Right. But now example 4. Now in Zn, your n is not a very small positive integer, but it's a big one, let us say. It's a big one. Then how do you talk about units? How do you talk about the number of zero divisors? So now the question given is the number of zero divisors of Z 2024 is. 2024 is this year. For fun, I have given like that. So let's now, the options are given to you. The 4 options are here. Very good. And now consider the ring Z 2024. You cannot physically go into the elements of A belongs to Z 2024 such that A comma all those A which are relatively prime to 2024, who are they? Go on writing them. It will take a long time. And then count. It will take a long time. So therefore, units, the number of units in Z 2024, I will use the formula phi of 2024. How do we calculate phi of the Euler's V function of 2024? So we normally do, we take 2024, write its prime factorization. The prime factorization is 2 cube into 11 into 23. So, right. So those are the prime factorization. Then phi of 2024 is equal to phi of 2 cube into 11 into 23. That is equal to 2 cube into 1 minus 1 by 2. into 11 into 1 minus 1 by 11 into 23 into 1 minus 1 by 23. That's the formula. And simplify. You will get 2 square into 11 minus 1 into 23 minus 1. That is 4 into 10 into 22. That is 880 units are there. The number of units in Z 2024 is 880. Now we talk about zero divisors. The zero divisors of Z 2024 are given by Z 2024 star, non-zero elements of that, minus the units of Z 2024. And why it is so? Because every non-zero element of Z 2024 is either a unit or a zero divisor. There is a print mistake. It's not Z14, it is Z 2024. So the number of zero divisors of Z 2024 is given by mod of number of elements of Z 2024 star, they are 2023, minus the number of elements, the number of units, that is 2024 minus 1 minus phi of 2024. This is 2023 minus 883. When you compute, it is 1143. So the number of zero divisors are in Z 2024 are 1143. That's a good question. It's a good question. And the answer is option 2. Now let's move on to the last question. I think, yes, it's the last question. This question has come in TS Set 2023 March exam from algebra, that is from on the units in a ring. The question number is 70 with this question ID. You have to find the number of units in the ring Z by 4Z, the quotient ring, cross, that is the direct product of these two rings, Z by 6Z. We are given 4 options. We have Z by 4Z isomorphic to Z4, Z by 6Z isomorphic to Z6. So first I will make a computation by the formulas, that is the number I will take. The number of units in Z4 are phi of 4, that is phi of 2 square, that is 2 square into 1 minus 1 by 2, that's equal to 2. In Z6, the number of units are phi of 6 is equal to phi of 2 into 3. 2 and 3 are relatively prime. Therefore, phi of 2 into phi of 3, that is 2 minus 1 into 3 minus 1, because 2 and 3 are prime. That is 2 only. So now Z by 4Z cross Z by 6Z, the direct product, isomorphic to Z4 cross Z6. The units in Z by 4Z cross Z by 6Z is equal to the units in Z4 cross Z6. Therefore, what are the units? The set of all those ordered pairs A comma B, where A is a unit of Z4, B is a unit of Z6. And how many? Z4 has 2 elements, Z4 has 2 units, Z6 has 2 units. Use the product rule, then you will get the number of units in the ring Z by 4Z cross Z by 6Z is phi of 4. A has phi of 4 choices, B has phi of 6 choices. Use the product rule, then 2 into 2, that is equal to 4. So that is the one. That means in this, the formulas we have used. But I will show you the same question. Because this Z by 4Z, Z4, Z6 are small rings, I can physically, count, physically get the units of those things and talk about the units in the direct product. Right. That's the same question. Right. So we have this, and now the units in the ring Z4, physically count them. all those A belongs to Z4 which are relatively prime to 4. What are the elements which are relatively prime to 4? 1, 4, 3, 4 is 1. Both are 1 and 3. So the units in Z6, physically count. What are those elements of Z6 which are relatively prime to 6? GCD of 1 and 6 is 1. 2 and 6 is 2, it is not relatively prime. 3 is not, 4 is not. 5, GCD with 6 is 1. So 1, 5. So the units are 2 here, and the units in Z6 are 2 here. They are these elements. Right. Now take the dot product isomorphic to Z4 cross Z6. And the units in the ring Z by 4Z cross Z by 6Z is the units in Z4 cross Z6 is the set of all those ordered pairs A comma B, where A is a unit in Z4, B is a unit in Z6. Write down. So it will be 1, 1, 1, 5, 3, 1, 3, 5. So physically we write down how many? They are 4 in number. So the number of units in this direct product Z by 4Z cross Z by 6Z is, you count them, 4. So that is the detailed discussion of this question, and the answer for this question is option 2. And that is the detailed discussion on the units in a ring from the ring theory, from the chapter algebra. And in this lecture we talked about units in an arbitrary ring, units in Zn, and zero divisors in Zn, and we have stated the important properties of it, and we have worked out 6 problems. Out of that, 2 problems have appeared in the TS set examination. I am sure that you have understood the concepts and the problems that I have discussed in this lecture. I have been doing the videos, mathematics videos related to JEE main examination and the TS set, AP set, JL, DL and CSIR net examinations. If you like my videos, please like, share and subscribe. I wish you all the best. Thank you.